It's time to talk about nuclear chemistry. Ready? All right, so what is a nucleon? A nucleon is a particle in the nucleus. So that includes two things, either a proton, which has a positive charge and a mass of 1 U, atomic mass unit, or a neutron, which has no charge, but also has a mass of 1 U, or atomic mass unit. So a nucleon is any individual particle that is found in the nucleus. A nuclide is a specific nucleus. So it has a specific number of nucleons, a specific number of protons, and a specific number of neutrons. So we can represent it in two ways. So we can use the notation seen here in the image, where you have the symbol, you have the mass number, and you have the atomic number. Or we can use the element name and mass number. So here we have carbon, atomic number, mass number 12, atomic number 6, but we could just say carbon 12 and write it like this. Okay, that is entirely possible. An isotope, right? Isotopes are atoms of the same element, but they have a different number of neutrons. So they will have the same number of protons, but a different number of neutrons. So same element, same number of protons. That's literally the only way to be the same element, because the number of protons defines the element. Hydrogen always has 1 proton. Lithium always has 3 protons. Oxygen always has 8 protons, okay? And then the number of neutrons can be different. So you can see in this example, how would I find it? So lithium 6, I would do 6 minus 3. So lithium 6 has 3 neutrons. But lithium 7 has 4 neutrons, and lithium 8 has 5 neutrons. Okay, not all nuclei and not all isotopes are stable. There is a band of stability, and the band of stability indicates, first of all, that any nuclei that has more than 83 protons is automatically unstable, all versions of it, okay? So if you look, here is number of protons 80, so a little bit past here, right? So right here, look at this. That's all unstable, radioactive, okay? All isotopes for those are unstable. So here you can see there's 83, right? So greater than 83, all of them. So all of these, and all of these down here, they're all unstable. How can I tell? Because the mass, the atomic mass, is written in parentheses. That means, I don't know, kind of a guess, but I can't really figure it out because all of them are unstable. They're all breaking down, okay? There are also 2 exceptions. You can see right here, atomic number 42 and atomic number 61. Their mass is also in parentheses, indicating all of their versions are also radioactive, but definitely greater than 83, they all are. Now, some isotopes with fewer than 83 protons are unstable and radioactive. However, these elements also have stable isotopes. So carbon, for example, has this version, carbon 14, that has a half-life and is unstable. But we have carbon 13 and carbon 12 that are stable, okay? So versions of elements with less than 83 protons can still be radioactive, can still be unstable, okay?
All right, so let's look here, and we're going to look at some stability. So watch this. If I'm going to put a proton in here, it tells me, oh, this is hydrogen, and I can just open these just so you could see what's going on. And it says that it is stable. If I add another proton, it becomes unstable. Why? What do I need to do to make it stable? Well, let's try and add, oh, look, when I add a neutron, it stabilizes it. We are not going to focus on electrons right now, but here I do want you to just see, do you see how the net charge is +2? That's because I have 2 protons, and I don't have any electrons to balance it, so that means I have a charge of +2. What if I add another neutron? Oh, it's still stable. is, remember, we always think about, for sure, a 1-to-1 ratio. So if I have 2 protons, I can at least have 2 neutrons. What if I add another neutron? Oh, now this is an unstable version, but it's still helium because I have 2 protons. Add another proton. Oh, wait, now it's stable. What if I add another proton? The name of the element changes, but you see it is unstable. If I add another proton, that doesn't help. So what do I have to do? Add a neutron? Oh no, add a neutron? Okay, so now we are 1-to-1. You see our ratio up here? What if I add another neutron? Still stable. What if I add another one? Oh no, now it's unstable. So we add a proton. This is carbon, right? So let's add a neutron. Now it's unstable. So let's add a proton, and let's add another proton to make it 1-to-1. So this is oxygen. So I have 8 protons and 8 neutrons. What if I add another neutron? Oh, still stable. Add another one. Oh, still stable. Add another one. Oh, now it's unstable. Okay.
All right, what happens when an atom is unstable, when a nucleus is unstable? Well, it will decay according to its half-life, whatever that time frame is. Will it decay in 39 seconds? Will it decay in 12 million years? How long? The nucleus, though, is going to break apart. It's spontaneous. It's natural. The nucleus will continue to break apart until it is stable. Decay will always, eventually, produce a stable nucleus. So that could occur in one step. One nucleus decays into a different nucleus, and now it's stable. It may occur in many steps. So look at this chain of reactions that must occur until we eventually get to a stable nucleus. So we'll continue to decay until it gets to stability. So what happens in nuclear reactions? When a nucleus decays, it's unstable, it breaks apart, okay? So a small fraction of mass is converted to energy, and this is unusual for nuclear reactions, but as a result, a huge amount of energy is produced. It may also release radioactive particles and radioactive energy, one, the other, or both, and therein it's problematic. Are you producing radioactive waste? Are you producing radioactive energy or particles that could damage human tissue? Okay. What are the types of nuclear reactions? Well, let's look. So we have transmutation. So transmutation means atoms of one element change into atoms of another element, okay, or an isotope. But it's going to change. The nucleus is going to change. Okay, the number of protons in the nucleus changes, the element changes, it changes. Transmutation. It can be natural, so which means it just breaks apart, spontaneous. Or it could be artificial, meaning the nucleus is there and I have to hit it with a particle and then it breaks apart. So for a natural transmutation, I have one reactant. It's just a nucleus and it falls apart. When it is artificial, I need two reactants. So I have this nucleus, but I got to hit it with a particle, and then the nucleus falls apart. But no matter what, natural or artificial, I start with one element and I end with a different element. One element changes into another. Fusion versus fission. Okay, so fusion versus fission. Fusion is when two nuclei join together and make a bigger one. Fission is one nucleus breaks apart into smaller pieces. So fusion occurs in stars, okay? And Fission occurs in nuclear power plants, also in some nuclear bombs. So you can see the difference between fusion, joining two little ones into a big one, or bigger. Fission, taking one big one and splitting it apart into smaller pieces. Okay, fusion, joining, fission, splitting. Okay. What kinds of particles are involved in these reactions? Well, table O is really our go-to because it could involve protons, neutrons, beta particles, also called electrons, you should know that, positrons, and alpha particles. And alpha particles are really just a helium nucleus, okay? What types of energy are involved? Well, again, table O is your go-to. And if you look here, you will see gamma radiation. How do I know that it's energy? Because the numbers on the top and the bottom are 0. So what you should know here is that the top number represents mass. Okay? The bottom number represents charge. In the case of helium and hydrogen, right, that also is atomic number. Okay, but for the other ones, it's going to represent charge. So mass and charge. Why does that work? Because protons have a positive charge, so it's also the charge attributed to the protons in the nucleus. All right, let's look at decay modes. So we need table N. All right, so when you look at table N, you could see some of these nuclides, right? A specific nucleus with a specific proton, specific neutrons, have alpha decay. What happens in alpha decay? Well, you have a nucleus that breaks apart and releases an alpha particle in the process and then transmutates into a new element. What about beta decay? Well, some of these have beta decay, so more of them in this little section here. In beta decay, same thing, that nucleus breaks apart and releases a beta particle and transmutates into a different element. And then we can have positron decay, right? So here's one right here. Positron decay is when the nucleus breaks apart. In the process, it releases a positron and it transmutates into a different element. Now, none of these are listed here, but you could be shown one on the exam like this. So some just release gamma radiation. They don't release additional particles, okay? They're just releasing that very dangerous gamma radiation. So which way will particles be deflected? Okay, so we can deflect particles using either a magnetic or an electrical field. Positive end and negative end. So it doesn't matter if they're asking about a magnetic field or an electrical field. We'll have to have a positive and a negative. And we're going to send a beam of particles like directly through here. Okay. Electrons are attracted or deflected toward the positive because electrons have a negative charge. Neutrons have no charge, so they just pass through completely undeflected. And protons have a positive charge, so they are deflected toward or attracted to the negative side. So let's look at that. It would look like this. You see gamma with no charge, undeflected. Beta, which is an electron, has a negative charge, so it's deflected toward or attracted to the positive. And alpha particles have a positive charge, so they are deflected toward or attracted to the negative, right? Alpha, beta particles, and gamma, okay? Now, what about penetrating power? Okay, penetrating power is the ability of those particles to pass through things. Well, alpha particles have a big mass. They have a mass of 4. So things just like paper can block them, okay? And then we have beta particles, and beta particles have a mass of 0, but a charge of -1. So they can get through paper, but something like aluminum is going to block them, right? And then we have gamma rays that can get through so much more because they have no mass and no charge. So there's nothing really interfering with them passing through things. So the penetrating power is least for alpha particles and greatest for gamma, because we're just going to compare alpha, beta, and gamma. All right, beta is in the middle. Now, what about ionizing power? So ionizing power is the ability for that beam of particles, whatever it is, to cause other atoms to lose electrons. Now, in order to do that, the particle has to have a charge. Okay, so alpha particles have a big charge. They have a +2. So they are great at causing other atoms to lose electrons. Beta particles have a charge. It's negative though. So they are kind of good at it. And gamma has no charge, so it's really not good at it at all. So alpha particles are the least penetrating power, but the most ionizing power. And gamma radiation has the most penetrating power, but the least ionizing power. So they're just reversed. Nuclear reactions have both benefits and risks. So certain radioisotopes have specific uses, and some are used in medicine, okay? You have to know these exactly, so learn them. So we have carbon-14. It's used to date organic material, called carbon dating. So things that were once living, so trees and animals. If we find bones, okay, carbon-14. Iodine-131 is used to treat thyroid disorders. So diagnose and treat. So iodine for the thyroid. Okay. Now, cobalt-60 and technetium-99 are both used in relation to cancer. And you don't have to know specific. You should just know they're both for cancer. So we have carbon-14 for things that were once alive, like trees and animals and humans. Okay. We have iodine-131 for thyroid. And then we have cobalt-60 and technetium-99 for cancer diagnosis and treatment. And then we have uranium-238, which is used for dating rocks and minerals, because the half-life of uranium-238 is so long, so it lasts, so we're able to date things that are older. Okay, things like technetium-99 and cobalt-60 and iodine-131 have a half-life that is appropriate for being used in a human body. Okay, we want a half-life that's long enough for us to be able to see results, but short enough that it's not continuing to release radiation my whole life. Okay. So what are some other benefits? Well, nuclear reactions produce a lot of energy, more than any other kind of reaction. So it doesn't matter, artificial transmutation, natural transmutation, fission, fusion, doesn't matter, produces a ton of energy. Nuclear energy is reliable. So actually, nuclear power plants run with very little interruption, and they need very little maintenance. And they are low cost once they're running compared to natural gas or coal. And in addition, nuclear energy does not produce carbon dioxide, so it does not impact greenhouse gases. But there are risks. So first of all, nuclear plants are expensive to build. They may be inexpensive to run, but building it, hugely expensive. Nuclear plants have to use a lot of water to cool the reactors. Remember, it's producing a lot of energy. A lot of it is heat, so we need a lot of water. Some nuclear reactions produce radioactive waste. And then what do we do with it? Like, nobody wants it in their backyard. Where are we going to put it? Exposure to radiation can be harmful to humans and the environment. Yes, it is used in cancer treatment, but at the risk that it could create more problems. Okay, so radiation absolutely is harmful. And there's the risk of accidents or meltdowns. If there's an accident or a meltdown in a nuclear power plant, it can have catastrophic, huge effects, negative, on the surrounding area. So there have been many that have occurred. And again, those effects end up being global, because it's not like the radioactive waste just stays right around Chernobyl and doesn't go anywhere else. It spreads around the world. So the amounts of radiation from all the nuclear bomb tests, from the nuclear accidents, from the bombs that were dropped on Hiroshima and Nagasaki, have worldwide effects. So the amount of radiation is increasing on our planet as a result. Okay. In class, we're going to do blue kit. So are you ready?